Welcome back to The Explainer. Today, we're diving into a seriously incredible architectural journey. We are going to travel all the way from the messy, physical, clacking world of 19th century telegraphs straight into the mathematical purity of the modern command line. It's a fascinating story, really, of how physical constraints literally birthed the pristine digital text environments we rely on today. So, to start us off, let's ask a pretty fundamental question here. What actually lies beneath the bloat of our graphical interfaces? I mean, we're all incredibly used to modern GUIs, right? The windows, the icons, the mouse cursors, the whole shebang. But at their absolute core, graphical user interfaces are essentially heavy, fragile, pixelated guesswork. Beneath all of that visual translation lies a sleek underlying reality of pure text-based computing. To describe that underlying reality, the command line interface, or the CLI, is often called an incredibly beautiful deterministic cellular matrix. And honestly, that hits the nail on the head. It's the purest form of digital truth. When you strip away all the graphics, every single keystroke you make in this matrix is a direct, unmediated signal. You're interacting with a picture, you're interacting with raw, discrete logic. Just look at this stark contrast here. It's wild. On one side, the graphical interface trades exactness for visual metaphors. But on the other, the command line gives you a 100% exact lossless fidelity log. Imagine your screen operating on a rigid monospace grid, kind of like evenly spaced chopsticks. By rendering just a single character on this exact, discrete grid, we completely bypass all the latency and bloat of those heavy graphical systems. All right, let's jump into part 1, the 5-bit telegraph era and its mechanical origins. To really grasp how we achieve this pristine digital grid, we've got to travel back in time a bit, to the surprisingly gritty mechanical origins of text systems. Back in 1836, Morse code used variable-length auditory signals. That was great for a human ear, sure, but mathematically, very difficult for a machine to parse. Then, in 1874, Émile Boudot patented a 5-bit multiplex telegraph. This was a real game changer because it introduced uniform-length binary sequences. That mechanical breakthrough set the stage, eventually culminating decades later in the 1963 ASCII standard. But, of course, there was a catch. Those early teleprinters running on the Bodo-Murray 5-bit code had some severe limitations. A 5-bit system is mathematically limited to just 32 codes, 2 to the power of 5. So to get numbers and punctuation, operators actually had to use stateful shift keys. They were constantly toggling back and forth between letters and figures. The absolute crucial point here is that this mechanical shifting completely blocked random memory access. An early computer couldn't just look at a piece of data and instantly know what it was. It had to read the whole tape from the very beginning just to figure out what shift state it was currently in. It was a total nightmare for early computing. Moving right along to part 2, the 7-bit ASCII breakthrough and the hunt for a stateless, unified code. Fast forward to the early 1960s. You've got this group, the ASAX3 committee, and they take on what is honestly a massive mission, designing a completely stateless, unified code for the rapidly exploding computer industry. The engineering compromise they ultimately reached is just fascinating. So why did they land on exactly 7 bits? Well, first off, 6-bit codes still required that highly unreliable shifting we were just talking about. Second, they looked at 8-bit octets, but those were simply way too costly for data transmission over the incredibly noisy phone lines of that era. So step 3, the 7-bit system stepped in. It provided 128 codes, which perfectly balanced the need for a full uppercase and lowercase alphabet, with the strict bandwidth limitations of the time. Let's ground this whole abstract data concept in physical reality for a second. Standard paper tape, which was used for memory at the time, physically held 8 punch channels across its width. The engineers took 7 of those channels for the ASCII data bits, and they brilliantly reserved the one remaining channel for parity, which is just a method of mechanical error checking. So the 7-bit code physically fit onto the medium of the day like an absolute glove. And all of this brings us to a very, very special number in the computing world, 127. Let me set up an incredible piece of historical trivia for you regarding the very final position on the ASCII table. Position 127 is the DEL, or delete command. In binary, 127 is represented as 7 ones, 111, 1111. And this brilliantly illustrates the real aha moment of physical computing. On a physical piece of paper tape, punching out all 7 holes literally obliterated whatever character was previously punched there.
If a human operator made a typo, they couldn't just patch the hole in the paper, right? So they simply backed up the tape and punched out every single hole, basically telling the machine to ignore that frame completely. That physical, mechanical reality forever made 127 the delete key. No way around it.
Okay, part 3, designing the code page and creating a logical matrix. Looking at archival X3.2 committee drafts like this one really grounds all that math in some tangible history. There was intense, painstakingly detailed debate over exactly where every single character, symbol, and control code should be placed on this grid. They weren't just throwing letters at a wall and seeing what stuck. They were architecting a highly logical matrix from the ground up. Just look at the brilliant logic they finally landed on here. It's like a giant puzzle they solved perfectly. They isolated all the control codes, things for hardware routing, at the very beginning. Hex positions 00 through 1F. Then they put the space character at position 20. Why? So it would naturally sort alphabetically before any actual letters. Genius! And they started the uppercase A at position 41, keeping the entire alphabet in a perfectly contiguous sequence. It was an absolute masterpiece of logical design. And because this grid was just so mathematically rigorous, it gave programmers the power to modify graphic subsets to support continuous logic loops. Keys like Control-C were designed to natively intercept terminal signals. Think about it. You press Control-C and it instantly sends a signal interrupt straight to the operating system, entirely bypassing the need for a mouse or any visual buttons. Now, to truly appreciate ASCII, you really kind of have to look at its main rival at the time, IBM's EBCDSE. ASCII gave programmers a contiguous, sequential alphabet from A to Z. It made it incredibly developer-friendly to loop through characters. EBCD, on the other hand, it had a fragmented alphabet with literal physical gaps in it. Why in the world would they do that? Well, because IBM was actively trying to preserve the structural integrity of physical punch cards. If you punched too many holes close together, the cardboard would literally fall apart. ASCII won because it was designed for pure logic, not cardboard. Which brings us to part 4, the command line and our deterministic reality. So, what does this all mean for us today? How do these rigid 19th century constraints actually impact us right now? Well, when you interact with the command line interface, you are compiling imperative text scripts directly into the machine's arithmetic silicon substrate. We really have to remind ourselves that typing in a CLI isn't painting a picture. It is feeding discrete, exact mathematical truths directly into the machine, without any room whatsoever for a catastrophic misinterpretation. All right, let's dive into one final kind of philosophical comparison here. We've got this stark juxtaposition between what we can call wet code and dry code. Wet code is traditional human language. It is highly relational, it's inherently ambiguous, and it's forgiving, mostly because we humans are forgiving. Dry code, which operates on this monospace grid we've been dissecting, is built on Boolean logic. It is binary, it is deterministic, and it is entirely cold. It absolutely doesn't care if you're having a bad day, it just perfectly executes the commands as written. As people like the cryptographer and legal scholar Nick Szabo have pointed out, this whole evolution from Baudot to ASCII proves something really profound. Yes, we can translate human intention into deterministic binary logic. That 7-bit grade gave us the ultimate mathematically pure infrastructure for autonomous execution, completely free of ambiguity. And that leaves us with this final, pretty provocative thought to ponder as we wrap up this explainer. As we continue to build our modern world on top of this perfect, deterministic ASCII grid, we really have to ask ourselves, is the inherent ambiguity of human language a bug that needs to be completely eradicated by perfect code? Or is that very messiness the vital, forgiving feature that actually keeps our human society functioning? Thank you so much for joining me for this explainer. I have a feeling you'll never look at the text on your screen quite the same way again.